Hello everyone! This is our first lesson in our unit on forces. So in this lesson we will be focusing on identifying what a force is and what momentum is and how they're related to each other, as well as identifying different specific types of force and being able to represent them using a free body diagram. So let's dive in. Let's start with the idea of momentum. So up until now, we have been talking about motion, about the velocity or acceleration of an object, analyzing objects that are moving. But a key additional understanding for us to add on is that anytime an object is moving, it has momentum. All right, and you've probably heard the word momentum used in everyday language before. And it's kind of hard to define. I kind of think of it as like the amount of oomph behind an object's motion, like how strong that motion is. And so it really depends on two things. One thing that influences momentum is how fast the object is moving, its speed or its velocity. But the other thing that influences momentum is the mass of our object. So more massive objects have more momentum because they're bigger, they're heavier, they have more oomph behind them when they are moving. So that's our basic idea with momentum. It's this quantity that measures the strength of motion depending on both mass and velocity. Now, because momentum depends on velocity, and velocity is a vector, momentum is also a vector. What does that mean? Again, a vector is any quantity in which direction matters. So when we're looking at momentum, we're also trying to keep track of direction. That's not going to matter too much yet this unit, but next unit it's going to be really, really important that we keep direction in mind as we are talking about momentum. Now we measure momentum in the very inelegant unit of kilogram meters per second, because momentum is just mass times velocity. Mass in physics, we default to the unit of kilograms. That's our standard unit for measuring mass. Our standard unit for measuring velocity is meters per second. So you multiply them together, you just smash the units together. Momentum is measured in kilogram meters per second. All right. And so we have our formula for momentum right here. Now the funny thing is the variable representing momentum is P, which seems kind of weird, but like M was already in use for mass, so we went to P. Yay. All right. So P equals MV really just means momentum equals mass times velocity. Okay. So to see kind of how we might use this in a sample problem. So say we've got a 150 kilogram ostrich, typical weight for an ostrich, is running at 15 meters per second because they are freaking fast. All right. How fast would a 5,000 kilogram elephant have to move in order to have the same momentum as the ostrich? So I'm going to go ahead and go through my guess method and list out what I know and what I don't know to start. All right. So I'm going to make two different columns because I got two different animals here. I've got an ostrich and an elephant. They each have their own information. So I'll separate those givens and unknowns out. So the first thing I know for both of these is the mass. I know the mass of the ostrich is 150 kilograms. I know the mass of the elephant is 5,000 kilograms. I also know that the velocity of our ostrich is 15 meters per second in some direction, all right? But we don't know how fast the elephant is moving. That's the thing that we are trying to solve for. Now, the relationship, the thing that links these two lists of knowns and unknowns together is the fact that both of these animals are supposed to have the same momentum. All right, so what that means is I can write an equation saying that the momentum of the ostrich is equal to the momentum of the elephant. I'm keeping track of each one separately by just using little subscripts to indicate which animal I'm talking about. Okay, so momentum of the ostrich is equal to the momentum of the elephant, and then momentum is just equal to mass times velocity. So I can rewrite this equation saying the mass of the ostrich times the velocity of the ostrich, which is its momentum, is equal to the mass of the elephant times the elephant's velocity, because that's the momentum of the elephant. So I can set those two equal to each other, and now I can start plugging in information here. So I know the mass of the ostrich, the velocity of the ostrich, and the mass of the elephant, so I substitute those values into the equation. multiply those through, and then divide both sides by 5,000 to get velocity by itself. And ultimately, I determined that the elephant would only have to move at 0.45 meters per second to have the same momentum as this sprinting ostrich, all right? So we're seeing two different things that are playing into momentum there for both of these to have the same momentum. The elephant has a big mass but a small velocity. The ostrich has a smaller mass but a bigger velocity, and ultimately those come together to multiply to the same momentum for each other. All right. So that's the idea behind momentum. And as we kind of talked about last unit, like, it would be lovely if everything just maintained the same velocity and the same momentum all the time, but alas, things change. Change is good, it's fine. So this brings us to the idea of force. So we all kind of have a general sense of what a force is. We know that it's like a push or a pull being exerted upon an object, but to really transform and elevate that definition to something worthy of physics and academia, we have to specify that the push or pull will tend to try to change the object's momentum. That is what a force does, that if you just have one force acting on an object, it's going to change the momentum of that object. And the way that it does that is by accelerating the object. So what I want you to start pairing in your mind are forces and acceleration. Okay, so like forces and acceleration are besties, okay? That like if you have a force acting on an object, that force is trying to accelerate the object. Now, a force doesn't necessarily always cause an acceleration if there are other forces that are like working against each other, and we'll get more into that in our next lesson. But for now, I really want you to be thinking about a force is something that tries to cause an acceleration. That's the big idea there. Okay. Now, force is also a vector quantity, just like momentum, just like velocity, just like acceleration, just like displacement. So direction matters. And force is measured in a new unit, which we call the Newton. And we abbreviate that unit with a capital N. Now, just to kind of contextualize what 1 Newton is, it is officially defined as the force required to accelerate a 1 kilogram object at a rate of 1 meter per second squared. Like, that's sort of weird. Like, I don't really have a strong sense of what that really means. So if you want to kind of understand it in more everyday language, if you imagine the force that it takes to hold up an object that's about 1/4 of a pound, it takes about 1 Newton of force to do that. Okay, so that just kind of gives you a general sense of sort of how big a Newton of force is. Okay. So then let's start thinking about what forces are acting in a particular situation. So we have this donkey. This donkey does not appear especially happy. These kids, I don't know what they're doing. But anyway, you can probably see that there are multiple forces that are acting on the donkey, different pushes and pulls, trying to, maybe get the donkey to move in one direction or the other. So take a moment and try to identify, like, what are the forces that are acting on this donkey? What are all the pushes and pulls that are happening to this donkey coming from outside of it? Well, I identify 5 major forces that are acting on this donkey, okay? There's the force of the kid behind the donkey who's trying to push it to the right, okay? So there's this pushing force from the kid in red. We also get this pulling force from the kid in green who's pulling on the reins of the donkey, trying to pull it to the right as well. So those are a couple forces that I see right away. A couple that I might be able to think about as well are gravity is pulling our donkey down, because gravity is always on, right? Earth always is drawing us to itself. Earth loves us very much, okay? And Earth loves this donkey, so Earth is pulling down through gravity on this donkey. But the donkey is not like then falling downward, because ultimately the ground is also pushing back up on the donkey, holding the donkey up, preventing it from accelerating down to the center of the earth, which, we appreciate. But that's not the only thing that the ground is doing. And to really understand the other contribution of the ground, you could think about how might the scenario look different if it were on ice instead of on grass, right? We see that there's also like a slipperiness or a stickiness factor there, that there is also a friction force that is helping to hold the donkey in place and counteracting the pushes from the kids, right? It's helping the donkey to kind of like grip the ground and resist those forces. And so friction is also exerting a force, ultimately to the left on this donkey, trying to resist that pull to the right. Okay, so I see 5 different forces then acting on this donkey, at least in the mechanical realm. We'll get into all the electrical forces and stuff later. But mechanically, we've got these 5 big forces, and those represent sort of our 5 big forces that we're going to be focusing on during this unit. Okay, so here are the different types of forces that we should be on the lookout for. Now, ultimately, there are 5 big ones, but they fall into 2 different categories. There are contact forces and there are field forces. Contact forces, as you might guess from the name, are forces that act through direct contact, okay? That can only be exerted if the thing exerting the force is directly touching the object that is trying to exert a force on. So there has to be like direct physical touching between the 2 things to have a contact force, all right? So some examples of contact forces are applied force, which we represent as F for force with a little subscript A. That A tells us that specifically it's an applied force that we are focusing on. And an applied force is any sort of push. So if I'm thinking about our donkey friend over there, the kid who's behind the donkey who's trying to push the donkey forward, I would call that force from that kid an applied force, right? Another type of force that is a contact force is tension force, and that's a pulling force. So if you have something that's being suspended from a string or a cable, or in our donkey case, the kid who's pulling on the reins to pull the donkey forward, that would be an example of a tension force. Another type of force, and this one maybe is like a new one to be thinking about, is what we call normal force, which is F with our little subscript N for normal. And that is a supportive push being produced by some sort of surface that is sort of supporting our object and pushing it outward. Okay, so like in the case of our donkey, the ground was providing a normal force holding up the donkey against the pull downward of gravity. All right, so that would be a normal force. A lot of times we'll see like floors and ground, like the ground is exerting a normal force on things, but normal force doesn't necessarily always have to be upward. It's really coming perpendicular out of a surface. So if, for example, I were like leaning against a wall, I know this isn't a wall, but we're gonna like pretend that it's a wall for just a moment, okay? So like if I'm leaning against a wall, the push back from the wall to support me and hold me up, that would be a normal force, but it's not directed upward, it's directed like sideways at me, kind of holding me up against the push against the wall. Okay, so it's always perpendicular to the surface that is supporting our object. And then our last contact force is friction. And friction force is a force that opposes motion between 2 surfaces. It prevents things from being able to slide past each other. It tries to hold 2 surfaces in place against each other. All right, so those are our big contact forces. We also have another category of force, which is field forces. And field forces can act at a distance. They don't require direct contact between 2 objects for that force to be exerted. It's this action at a distance, okay? What force that we looked at for our donkey is a field force then? Yeah, so gravitational force is a field force that ultimately Earth's gravity always pulls us down whether we are physically touching the ground or not, right? Which is good, because otherwise like you would jump up and like you would never come back down again. Right? Because like as soon as you would leave the surface of the Earth would stop pulling on you and then you would just be stuck floating. Actually, that sounds kind of cool, but you know, not the way things work, in fact. And so gravitational force is an example of a field force that can act without direct contact. Another word for gravitational force is weight. All right, so anytime you hear weight, also be thinking of gravitational force. Like those are the same thing. They're synonymous, okay? And so we represent that with F with a little subscript G for gravitational, right? And then there are a bunch of other field forces, electrical, magnetic forces, we're going to get into that later, like next semester, all right? For now, the only field force we really need to concern ourselves with is gravity. So then kind of thinking about all of that and these different types of force, I want us to come back to this idea of like, if you toss a ball upward, what forces are acting on the ball, like while it is while it is like in motion, like going through the air, except we're going to pretend the air is not there. Like, what are the forces that are acting upon it? Just gravity, right? That's the only force acting on the ball. As soon as it leaves your hand, you cease to be exerting a force on it. I know that people often have this idea that like while the ball is on its way up, it's still got that like throwing force behind it. But the fact is, you cannot shoot forces out of your palm. I can't either. It's okay. It would be awesome, but that day has not come yet. All right. So since that throwing force, that applied force is a contact force, as soon as the ball leaves your hand, you are not exerting a contact force on it anymore. You're not exerting that applied force on it, which means that the only force that can be acting on the ball while it is moving up and back down again is gravity. Gravity is it, okay? Now, what people often think of as like, oh, it still has this like force that's pushing it upward. It doesn't have a force. It has momentum. It's moving up, but again, forces cause acceleration. There is no force that is accelerating the ball up once it has left your hand. The only force that is accelerating the ball is gravity that's pulling it back down again. Okay, so I know that one can be a little bit tricky, but just to try to help illustrate the difference between force and momentum. An object can have momentum anytime it's moving, but if it's not accelerating, if it's not really being like pushed in a particular direction still, it doesn't have that force acting upon it anymore. All right, so speaking of that gravitational force, that weight, weight depends on two things. It depends on mass, but it also depends on gravitational pull. I know a lot of times we use like mass and weight sort of interchangeably, which makes sense because the two are proportional to each other as long as we're here on Earth where the gravitational pull is pretty much always going to be the same. But once we start looking at like different locations, different gravitational strengths, etc. When we start getting into like other planets and other, like star systems and stuff later in the year, it's going to be really important for us to keep track of the difference. So I really want to highlight that for you now, that weight and mass are not the same thing, but they're related to each other by the equation that you see here, that the weight of an object is equal to its mass in kilograms times the acceleration it experiences due to gravity. And here on Earth, that acceleration is 9.8 meters per second squared for all objects, okay? So weight and mass, proportional, related, not the same thing. And we want to be really careful about that during this unit, okay? So we're starting to separate those out in our minds. Okay. The last thing I want us to talk about is free body diagrams. So now that we know that there are all these different forces that can act on an object, there's applied force, tension force, friction force, normal force, gravitational force, all those things, it can be a lot to keep track of. And so what we like to do is draw pretty pictures that illustrate all of those forces so that we can keep them all straight in our minds. We call those pictures free body diagrams because that sounds much more impressive. Okay, but it's just a picture of an object and all the different forces that are acting on it. And those forces are represented as arrows to show us the direction of that force. So let's practice with a few of them. Okay, so first one is if we've got a pendulum bob. I know this isn't actually a pendulum bob, but it's the closest I have right now. All right, so we have some mass hanging from a string. What are the forces that are acting on it? I see two big forces acting on this pendulum bob. One is the gravitational force. Earth is pulling down on our pendulum bob, but our pendulum bob is not accelerating downward because there is an opposing tension force pulling up on the bob at the same time. So two big forces, gravitational force down, tension force up. Second example, if I have a chair and I am pushing it to the left, what are the forces that are acting upon the chair? I see four big forces acting on our chair. Of course, there's gravitational force because the chair we're assuming is on Earth, and so Earth is still pulling it downward. And then similarly, there is a normal force from the floor pushing back up on the chair to support it against the pull of gravity. There's also an applied force because I am pushing on that chair, and so I am exerting this applied force to the left on the chair. But simultaneously, the floor is resisting that push and trying to keep the chair in place on the floor, and that force is friction force. So if I'm pushing the chair, trying to get the chair to move to the left, Friction force is trying to oppose that motion, so it is pushing the chair back to the right. Right? And so friction force just changes direction, like depending on which way things are trying to move, it will just automatically like try to thwart that. Friction is the thwarter of motion. All right. Last example, if we have a block on a ramp, what are the forces that are acting upon this block? I see three big forces acting upon this. Of course, there is still gravity, and gravity is pulling our block straight downward. All right, even though it's at an incline, whoop, straight downward is that gravitational force. All right. There is also then a normal force that the ramp is exerting upon our block. And again, normal force is always going to be perpendicular to the surface that's supporting our object. And so it's kind of going out at an angle right now because our surface is at an angle as well. Okay, so we can see that normal force is pointing straight perpendicular out of the ramp that the block is sitting on. And last force then is the friction force, that ultimately the surface of the ramp is trying to resist that motion of the block sliding down, and so friction force is working against that downward tendency of motion there. Okay, so the block would tend to try to move down the ramp. Friction force will thwart that and push the block back up the ramp. And it should be noted then that friction force is always going to be parallel to the surfaces. Okay, so normal force is always perpendicular. Friction force is always parallel to the surface that's exerting that force. All right, let's check your understanding. We got a cat sitting on a shelf, all right? Start by drawing a free body diagram. What are the forces that are acting on our cat? I see two. I see a downward gravitational force because Earth loves this cat, and the cat is not like plummeting to the center of the Earth to its doom because we have the wooden shelf exerting an upward normal force on this cat. Second question, what is the mass of the cat based on the information that we have? All right. So I see here, I've got the weight of the cat. It's 80 newtons, which is approximately 18 pounds. So this is like a big old cat. I realize the picture, it's not that big a cat. Whatever, this is what I was able to find. Okay, so I know the weight of our cat is 80 newtons. All right, important that I use newtons and not pounds because I want to stick with sort of like standard physics units here for the equations to work. Okay, so 80 newtons there. And presumably this is an Earth cat. Cat's on Earth, which means that it has a gravitational acceleration here on Earth of 9.8 meters per second squared. That is the rate at which Earth is trying to accelerate the cat were it not for the shelf holding it up. So that's our gravitational acceleration. We are solving for the mass of the cat, and we have our equation that relates mass and weight. Fg equals mg. Weight is equal to mass times gravitational acceleration. All right, so I plug in my values here for weight and for gravitational acceleration, divide both sides by 9.8 to isolate mass by itself, and I get ultimately that this cat has a mass of 8.16 kilograms. That is all. That was a lot for introducing forces, so we'll continue to discuss and practice with it. Thanks, folks.